All right. And okay, real high level SLAM, simultaneous location mapping. So the particle filter requires us to map or match our sensor readings with what we get. That expectation comes from the map, right? And so what happens if we don't have an accurate or detailed map of the um, area, or that the environment changes faster than we can maintain maps, right? So the book, the authors in the textbook kind of take the approach that, oh, we think that having these high fidelity, high definition maps that are constantly updated in the cloud and then stormed out are kind of essential part of the process. But there's a lot in robotics and in autonomous vehicles that use SLAM and stuff. So the idea here is that now we're going to have not just uncertainty for movement and measurement, but also uncertainty on what we expect to be around us, right? So we're, not quite hopeless. We're basically going to build up a map while exploring an area, and then we're going to explore that area in a way that helps us kind of revisit areas and kind of refine the map as we go. And we'll have a process that tries to simultaneously reduce the errors, right? So, all right, so this is typically split into front end and back end to help us kind of simplify or think through this process. The front end is responsible for taking our raw sensor data and converting that, processing that into. Am I not sharing my screen? I just realized. Let's see, someone messaged, right? Yeah, okay, yeah. As soon as I heard that beep, I realized, oh yeah, I'm not sharing my screen. All right. Screen, just gotta go full screen again. All right, let me go back. Okay, so simultaneous location mapping. What happens if we do not have an accurate or detailed map, or it changes faster? We can build up a map while exploring that area. So now we have the front end, and that front end is going to process sensor data and some intermediate representation, right? So we're going to take that raw sensor, and we're going to consume that and transform that into things we call constraints and probability distributions and other information that the back end can use. Now the back end is now going to basically solve that state estimation or whatever type of optimization problem using the intermediate representation. Right? So, all right, so there's a number of different approaches to these that can actually involve Kalman filters and particle filters, but today most approaches are based on graphs, and there's two kind of dominant approaches out there. There's the pose graph and the factor graph. We'll talk just briefly about the pose graph, and we won't talk about the factor graph. So in the pose graph, I should maybe briefly explain what a graph is. I think hopefully most of y'all have some idea of what a graph in computer science is, but I'm not sure in like the electrical engineering or even computer engineering curriculum if it's covered explicitly. So what is a graph? A graph is um, uh, composed of nodes and edges, and the edges connect the nodes, and in such a way that it relates some information between them. And you can have different types of graphs. They're fairly generic. Kind of the graph came into its own with social media. It's of course been used for a long time, but Facebook Friends Network, as at least in the beginning, was modeled as a graph type of thing, and that's kind of how that whole social media as done by Facebook evolved, right? Where each node would be a person, and then they would be friends with each other through these edges, right? So the edge would relate their friendship status. So so in this case, though, our nodes of graph are poses at a certain time, right? And we might get that from telemetry, right? So we're going to explore this area, and so at each time step, time sequence, however we're going to sample that, we're going to have a pose represented in this node of graph, right? And since we don't really have much other way of figuring out where we are, because we don't have a map yet, we're going to do this from telemetry. And if you're outside, maybe you can use GPS or something like that, right? But if you're inside, in a robotics type application, kind of a stereotypical robotics application, you might have to derive all this stuff from telemetry, right? And then our edges are our spatial relations representing constraints. Okay, so for example, or in other words, multiple nodes, remembering that that's a pose at some time, might perceive a landmark, the same landmark, but from different perspectives, different locations, different perspectives. If you can match up those perceptions, maybe the front end is processing that data into these intermediate representations. If you can kind of match up and say, oh, these different nodes are all taking the same feature in the space, right? And we'll call that a landmark. And but since they're at different locations, likely at different locations, they're observing it from different perspectives. So we can represent those as a constraint. And then the way this process works is that we're going to try to transform one node perspective to another node's perspective, and we can do that using affine type transformations, again beyond the scope of this lecture, but basically we can take that let's say image that we have sensed. Maybe it's a camera image, or maybe it's a LiDAR image or something, right? But it's a data. And we're going to transform it based upon what we think we need to align it with a perception of that landmark, right? So if I'm looking at a, let's say a corner from one node, and I'm seeing it like that, but then at another time I'm seeing it from here, right? So I want, so this guy's going to perceive it differently, right? It might look something more like that. Oh, I have no idea actually. But what we want to do is we want to kind of take this um, constraint or obstacle and transform it so it matches up, right? So we're going to move this point over to there, and this point over to there, this point over to there. And as we do that, we're kind of moving this guy also, right? So this is all um, transformed together. And then when we're done, hopefully this guy now aligns with this in our computer representation of the data. And now this guy is over here. Now we can decide, you know, should those line up together, or are they offset some, or something like that. So we're going to observe some errors associated with that. And we're going to use a optimization technique, and we're going to minimize those. How do I undo that? So we're going to minimize the errors of the nodes with respect to these constraints. And with this optimization technique and the least squares approach, will minimize the set of errors, right? So the squared errors. So it doesn't matter whether they're plus or minus errors, right? So all right, so that's super high level SLAM, and I will kind of apologize. It's not really an apology, because yeah, we have to make decisions on what we can cover, and it doesn't mean SLAM's not important, but just trying to squeeze everything in. All right, so let's start talking about sensors now a little bit. So we've been talking about concepts, algorithms, all these different filters and stuff. Let's get back to talking about some hardware and signal processing maybe. So, all right, so how do UAVs perceive the world? Millimeter radar. Won't get to these. I've got some stuff in the slides right now in this presentation, so feel free to look ahead. But in all cases, I tend to update things as the lecture date gets closer and stuff. So expect these slides to be further enhanced. All right, perception overview. Perception involves both understanding the ego vehicle status. We've been talking a lot about that, but also other objects around it. The next few lectures, and I'll focus on other objects, not exclusively, but there is a lot of considerable overlap. All right, and so just kind of my way of thinking about it. Perception process involves two steps. The sensors are going to collect raw data, and then we'll use some algorithms. Might be machine learning type algorithms. They might be reinforcement learning algorithms. But they're going to combine and process that data to produce insights, right? And deliver those insights in a consumable form to some other part of the system that needs it, right? And so when you think about sensors, sensors are probing the physical world, right? And so there's something out there in that physical world, and we're going to use physics to kind of probe that. Now, sometimes we use reflections of electromagnetic waves off of things that have different conductivities and permittivities and permeabilities and whatnot, and that cause that wave to be reflected and stuff. So hopefully that draws some memories from your electromagnetic fields class, whatever that's called. I taught that once. I can't remember what we call that, but then everything else is transformation, right? So once we probe that physical world, we might change that into, we might uh, sense that via voltage or frequency or something like that, and then we might need to transform that and digitize that, quantize that, and then filter it and that type of thing, right? So, but ultimately we're producing some raw data that is consumable by these algorithms. We're going to first focus on the sensor hardware and the signals coming out of them. And note also that these sensors also supply data to localization algorithms. So if you're wondering how do we get all those measurements in that particle filter or whatever, well, we'll eventually get to that. So, all right. So we'll, common sensors, I crudely break these up into some sort of time of flight measurement, and imaging or cameras, I'll just call it, right? So this is an active type of thing. This is more passive, but not strictly speaking, right? So, all right, so you guys are probably even had hands-on experience with little ultrasonic sensors that you plug into an Arduino board. They cost, tiny amount of money, and but they're pretty crude in terms of performance. We'll talk a lot today about radar, and then there's also a version of radar that's LiDAR, basically using a laser of some form, quality, or something, right? So, but these are all based upon the idea of emitting some sort of signal that probes the environment. It gets reflected in one way or another, and then comes back to most likely where we transmitted it from, very, very close by. Not always, but in these type of situations they do. And then we receive that. We tend to compare the time at which we sent it out with the time that it arrived back, and if we know the propagation velocity of that wave, sound wave, radar wave, radio wave, or light wave, then if we know the velocity through that whole process, then we can calculate how far away it is, right? So, and if we have some directionality to our system, we can also get some idea of the bearing, right? So, and there's tons and tons of tricks in all of these technologies to refine these things, right? So, camera now here, or this imager, is mostly a passive device. So fundamentally, you might just have one camera. It might have a bunch of pixels. I think we're all, super familiar with this technology these days. But you'll get likely an RGB value out, maybe infrared, and it's organized as a set of pixels, right? So, but we can, and so that those pixels are a 2D array, right? So we're getting a flat image out. We can perceive depth using stereo to two cameras separated by a little distance, and then we can do some disparity map work. Intel has a whole lot of cameras. They're not the only ones, but they're kind of dominant supplier of these things that actually will have a very simplistic LiDAR in it, and they wouldn't want it to be described as simplistic, but it's integrated with the imager, and so it's actually now an active device, and it's doing some sort of time of flight measurement. And then there's also this idea of sending out kind of a structured light or coded light is basically sending out a pattern. We'll talk a little bit more about this, but you send out a pattern and shine it out there, and you see how that pattern might be bent when it reflects off of let's say, a round object or something like that. So you can perceive depth that way. All right, so I'm going to dive into these millimeter wave FMCW radars, frequency modulated continuous wave, and some of this, you could translate to other type of time or flight type measurements, but there's a lot of unique things that are done with these, and I find it fascinating. So I'm going to burden you with it. So these provide an accurate and precise range, maybe not as good as LiDAR, but it is certainly better than sonar or ultrasonics. Angular resolution in particular is not as good as LiDAR, but performance continues to evolve. I did uplink a link to a video from TI, Texas Instruments, who's a big manufacturer of these, that talks about cascading multiple systems together to get some imaging. And so there's some interesting stuff there. It does have the advantage is that it does penetrate some obstructions better than LiDAR, like fog and rain. Doesn't penetrate through everything, but or otherwise it would never reflect back to us, right? So in particular, it can be used for cruise control. Whether it can be used for real imaging type applications is debatable, but yeah, STI. But if you ask Elon Musk or some of these others, Elon's going to rely on cameras, and the Waymos and cruises are kind of more prototypical autonomous vehicles are using LiDAR. All right. So what is this beast here? So they by millimeter wave, they're allocated to operate in these spectrums, and you'll find chipsets in these frequency ranges. It uses a linear frequency modulated chirp, okay, of a continuous wave signal. Right, it's not fully continuous wave. We're going to start transmitting here. This is time, and this is frequency here. And so this signal, this would be an up chirp. So it starts off at the beginning of the transmission at a low frequency, but then as time goes on, the frequency ramps up linearly, right? And then we'll typically kind of reset and then repeat and reset. So this kind of look like a little sawtooth wave, except it's not amplitude versus time, it's frequency versus time. But the amplitude is constant. And within this transmission time, we're not sending out a bunch of little pulses, we're sending out one continuous wave. But that is constantly changing frequency. So we transmit that out. It goes and reflects off something, maybe a car, maybe a pedestrian, maybe a cyclist. And then based upon its radar cross-section, okay, which is a function of how its conductivity. It's basically the difference in the transmission medium, right? So this is free space. So it's going to have free space permeability. Permeability doesn't affect us that much, but permittivity and conductivity, right? And then it's going to hit this car. Well, it's got a lot of metal in it, so it's going to have some finite conductivity, and it's got some glass and plastic, so permittivity's rubber permittivity is going to be different than air. So all that's going to cause a reflection, right? So just standard wave theory, you change change the permittivity and connectivity, you're going to reflect some of that energy. It's going to roughly obey Snell's law, kind of from a simplistic standpoint. So if it hits it at a kind of normal angle, it'll reflect straight back. But if it hits it at a more oblique angle, it'll reflect elsewhere. But there's enough energy, there's enough complexity in these things that it's going to reflect back to the source, right? So this isn't to scale here. These antennas are usually, essentially co-located, and this car is far away. So these rays would, in reality, be almost parallel, but traveling in different directions, right? So now we receive it. We might amplify it, filter it, that type of thing, but then we mix it in this non-linear device here. Might be a set of diodes and some wideband transformers, but it's a highly non-linear device. And if you haven't had communication systems or an RF course, microwave course, maybe you haven't seen this yet, but a non-linear device is going to take this cosine and multiply it by that cosine, or maybe it's a cosine plus j sine if it's complex, and a cosine plus j sine there. If you think about it, think back to your trig identities and your sum and difference equations, right? So you would end up with like cosine times cosine minus, or cosine times sine minus sine times cosine, or cosine times cosine minus sine times sine, depending on which one you're working with, right? So what you see here is that multiplication, that nonlinear. Okay, I should back up. And if we take this nonlinear and express it as a Taylor series again, you see that there's a squared term in there. So we're multiplying these signals together to each other. And so I cover this in more detail in my communications course or my microwave course. But what you end up with out here, if you go through all that math with those trig identities, is that the signals at the output of this nonlinear device are the original signals and the squared terms, but also the sum and difference, right, of frequencies, right? So if you have an omega here and an omega 1 there and omega 2 there, then you're going to have omega 1, a signal that is has a frequency of omega 1, a signal that has a frequency of omega 2, a frequency that has a signal of omega 1 plus omega 2. And the one we're really interested in this application is omega 1 minus omega 2. Or it might be omega 2 minus omega 1, right? So in this case, I think it'll be the first, right? Omega, the transmit frequency minus the receive frequency. The other one ends up in the negative domain, and that's okay, right? So so the key here is that the IF is the difference of the input frequencies. All right, so why does that matter? Well, here's our chirp when we transmit, right? So we'll call this beginning of transmission is time 0, and this is the length of our transmission or chirp, right? So then this waveform gets transmitted and it reflects, and sometime later it comes back, right? and now is presented back to this mixer, right? So as we're transmitting, we couple that transmitted signal, we sample that off, and we couple that to the mixer, and then we also couple the receive signal, right? So, you know, until we get a receive signal back, not much is happening, right? But once this receive signal comes back, you see that it's shifted in time as we would expect, right? It takes some finite amount of time for that signal to go out and come back, right? But when it does, this signal, when it first starts to be received, is at its lowest frequency, right? It's just starting its chirp. But in the meantime, while this wave has been traveling out there and coming back, that signal at the transmitter port of that mixer has already ramped up in frequency, right? And it continues to ramp up just as the received signal ramps up. And since these are linear chirps, if we're ignoring any Doppler effects, the frequency doesn't change with respect to where it is at within the chirp, right? So it changes, of course, with time, but you know, this initial point is the same frequency as it was here. This ending point of the chirp is the same frequency as it was when it was transmitted at the end of the chirp, right? So if we just look at these, you know, beginning, end, and midpoint, we see that, oh, this difference is all the same frequency, right? It's a constant frequency. But what if we slid this thing over farther, right? And where did my pen go? And we have a little bit later delay, right? And now we've got a longer, you know, longer time corresponds to further distance, corresponds to a bigger frequency difference, right? So we see that this frequency difference is related to the distance that object or target is. Okay, so here, what are our key points here is that we're transmitting this linear chirp. Its frequency varies linearly with time, right? Signal reflects off the objects according to their radar cross-section. And the received signal is simply a delayed copy. Okay, it's attenuated, got noise, but it's a delayed copy. We can amplify it and filter out some noise. The delay corresponds to the round trip distance. It's got to go out there. It's got to come back. All right, so there's a factor of 2 involved in that to convert the distance to a round trip distance and vice versa. At any given time where these signals overlap, the frequency difference between the signals is directly related to the delay. Okay. So now, if we want to figure out what is our range, right? So how do we calculate that, and then what is our ability to resolve that, right? So where these signals overlap, we have a valid IF signal. Note that these chirps, the way they're designed, is that they are tending to transmit longer than the round trip delay is, right? So this is the round trip delay, but it's much longer, right? So we have some significant overlap here, right? That's going to create at the IF this single tone frequency, right? So here it's a chirp, Here it's a chirp, but if we look at the difference, it's a single tone. So constant frequency. Where that frequency now is, we'll call it S of tau, right? So we have this as a slope, okay? And so we take this frequency and multiply it by the speed of light, or speed in the medium, and divide that by 2 because of the round trip distance, and factor in the slope, and we get the distance. Really, so what we're to derive this, we're just noting that, okay, the what we're trying to find is what we're measuring is this frequency here, okay, but that is representative of this tau, which is the round trip time, and then through this speed of light we can convert that into a distance, and we've got a factor of 2 along there to account for converting it into a one-way from a two-way trip, right? And this frequency represented by this S of tau gets converted to time via the slope of this line. What's sometimes called the chirp rate, but it's just frequent delta F divided by delta T there. So all right, so now we know how to transform that frequency measurement into a distance. So kind of makes sense to use the Fourier transform to be able to do that, right? And I mean, we could count the use a frequency counter to count that, but FFTs are easy to do once we're in the digital domain, once we sampled it, and it's also, you're going to see, we're going to use Fourier transforms about 3 times in this process. So our targets at different ranges produce different frequencies. So we can use Fourier transform to separate tones, right? So here we have 2 tones that are widely spaced, right? And so we do this Fourier transform, and then we look in these bins associated with this Fourier transform. We do some magnitude checking and maybe have a threshold or something like that, and say, all right, if we're above a threshold, that means there's a target there and there's a target there. We can take the frequency that's assigned to that bin and use our equation from the previous page, previous slide, to convert that into distance, right? So now, what happens if they're too closely spaced? Well, they bleed together, right? So our delta F is our ability to resolve these things is approximately equal to 1 over T sub C. Okay, where T sub C is the length of our chirp here, right? So I define that here in this graph. So if we look at that transmission, so T sub C. All right, so quiz time. I'll just open up your mic, or raise your hand, or type it in the text box, message box. Why? Where did I come up with that right there? Keep that. So anyone want to hazard a guess at or more than a guess of why? Where did I come up with that relationship? Can you all hear me? All right. Well, what do we know about Fourier transforms. All right. So hopefully from your signals and systems class, maybe your second semester when you did some sampling, and I don't know if you actually look into a fast Fourier transform algorithm, but hopefully you did discrete systems, and you look at some of the trade-offs with Fourier analysis, right? So depending upon our sampling frequency, that shows how high of frequency we can resolve without aliasing, right? So that's an important factor. But the length of the signal that we look at determines our frequency resolution, right? So it's Fourier transforms interesting because it in the time domain we have lots of time resolution but no frequency resolution, right? If we look at time, look at a signal in time, might be composed of all sorts of different frequency components, but they're all mashed up, right? They're all combined together, and we just see this signal wiggling around in amplitude with respect to time. So we can divide that time as much as we want. We have infinite time resolution, right? But we have zero frequency resolution. Then we go through the Fourier transform, and now suddenly, magically, we have potentially infinite frequency resolution in the spectral domain, but no time resolution, right? So if our signal varies in time, we don't perceive that in the spectrum. All we have is amplitude versus frequency, right? And we can divvy up that frequency and get better and better resolution, but we don't have any time resolution. Now, wavelets and other type of transforms maybe give you a trade-off, but that's the interesting thing about Fourier transforms is they trade off completely resolution from one domain to another. So it's an easy way of kind of thinking about it. I think that the frequency resolution out of a Fourier transform, a discrete Fourier transform, is a function of the length of your sample or your signal that you're bringing in, right? So if you can observe the waveform for longer, you can get more information about its frequency components and drill down more precisely. So, so if we want delta F to be nice and small, right? So if delta F was a little bit smaller, maybe we could resolve those peaks in this second case, but they're just too closely spaced right now. And so if we want that to be smaller, we want TC to be larger, right? So larger TC then will give us better frequency resolution. Well, it's not quite, because it's really maybe TC minus tau, right? But tau varies depending upon how far away the target is. So it's a kind of an approximation. We're saying that it's approximately proportional or related to 1 over TC, right? So that is a design parameter. We can, if we need to resolve a certain set of targets that are spaced closely together, maybe we want to be able to pick out individual pedestrians that are maybe coming to us on the side of the road or something like that, or bicyclists, and we want to separate out individuals there, then we need a certain amount of certain amount of frequency resolution, which translates into spatial resolution, right? So let me go full screen again here. So, all right, so we can start with the desired spatial resolution, transform that to our frequency resolution through our chirp rate and or slope of our chirp, and then calculate the TC that we need to achieve that, right? So really, another way of saying it is that we want our delta F to be delta F is greater than 1 over TC in order to be able to resolve, right? So if the tones are spaced closer than that, we won't be able to resolve them. We would do a peak search through this, right? To try to resolve these things. So here there's clearly an inflection of the slope. It goes from positive to negative, and then positive to negative, right? So we can determine that's a peak and that's a peak. We do some threshold there as far as an algorithm. Right, so to design the radar for a certain range resolution, we see that this TC is related to the bandwidth of the chirp, and ultimately that's what's going to produce resolution, right? So this is important in all kinds of radars, right? So if you're doing a missile tracking radar or something like that, and you want to find out if there's one missile coming at you or 100, then yeah, you need to be able to resolve those spatially, and that requires a wide bandwidth radar system, right? So the bandwidth of our chirp needs to be greater than C divided by 2, and then this is a delta distance, the change in distance. That's our spatial resolution. So simultaneously, the in hardware, our IF bandwidth and the sampling frequency of the ADC, is going to set the upper bound on a distance, right? Because this whole bandwidth and chirp needs to fit within that IF bandwidth, and then it's got to be sampled such that there's no aliasing and that type of thing, right? So these get harder to implement in hardware and more costly as they increase, right? So there's some hardware, maybe it's driven by cost or power consumption or just technology, right? And so there's some upper bound on that, and that's going to set an upper bound on the distance that we can image also, right? Because remember that the bigger this Dmax is, the greater that frequency difference is going to be. But that tone still has to fit within that IF bandwidth, and it still has to be sampled without aliasing, right? So, so there's an upper limit, and then there's a resolution limit here. So we're starting to be able to relate system objectives. Let's say a regulatory agency says you've got to be able to distinguish these objects at a between each other at a certain maximum range or something like that, right? And so or maybe marketing gives you those objectives and stuff, or maybe other parts of the system do, right? And now we can design our chip accordingly, or chirp accordingly, right? So all right, so now we can resolve things at a certain range, but what if we have multiple targets at the same range, right? So here's our ego vehicle, and these are potential targets. I've drawn them such that they're the same distance away, right? So they're all going to overlap in that Fourier transform. We're not going to be able to distinguish those. So let's work towards a solution to that. First, let's understand that, well, you may have caught that I only use magnitude of the IF signal in our previous slides, right? So, but we know that if we take a Fourier transform of a real signal, we will end up with a complex result in the spectrum domain. A lot of times we just take the absolute value of that and, oftentimes take log base 10 and then multiply by 20 to convert everything to dB, right? So, and we're throwing away phase when we do that, right? But let's now examine, is there anything we can do with the phase? So realize that our IF signal now is this cosine weighted by some amplitude, all right? We're not terribly worried about that. That does tell us a little bit about the size of a target or its radar cross-section, technically, scaled by distance or affected by distance or whatever. But really we're interested in these terms, right? So we've used this term, right? The frequency here, where of this cosine wave coming out of there, signal, is this slope times round trip distance divided by c, right? So that again, the slope translates the frequency and the time, and then the speed translates this into distance, and 2 is a round trip conversion, right? So so those are related. We've used that. Now what about this phase, right? So it turns out that if we can relate this distance to phase, then that's pretty interesting, right? So phase goes through an entire cycle in one wavelength, right? So there's 2 pi here. So it goes through 2 pi radians in a wavelength. And so we can look at the fractional distance relative to a wavelength produces some phase shift, right? And so there's this factor at 2 for the round trip is in there, but also there's a 2 pi there, right, for 2 pi radians. So this is the fraction of the full cycle, which is 2 pi, and gives us a certain phase shift. Now, that'd be in radians, convert that to degrees if you need to. But so, for example, at 77 gigahertz, a 1 millimeter change will produce about 180 degrees of phase shift. But if we just looked at this term, the impact on this term, that would only shift 333 hertz. Okay, I didn't double check these numbers, but I'm pretty confident in them. That's a really tiny amount, right? When we're talking signals that are starting off at a gigahertz, and yeah, we're measuring the difference IF frequency, but that's still pretty big, right? And 330 hertz, 333 hertz is really small. So, but we get a lot of phase shift. Now, yeah, we can have some ambiguities if we start wrapping around and stuff, but what can we do with this? So it turns out the starting phase of a signal is preserved through the Fourier transform as a phase at the peak. Okay, so we can get an estimate of the phase of this IF signal by looking into Fourier transform and at that peak, right? So then if we wanted to measure velocity, let's send 2 pulses, measure the phase difference between the 2, right? So we'll send a pulse measure the phase at that peak, right? So we got to find the peak and then measure, look up the phase at that point and save that. Send another pulse, do the same thing, find that same peak, look at the phase at that point and that bin of the Fourier transform, and then form a difference between them, right? That's that delta phi. We'll call this an omega there. Might be a little confusing, but it's commonly used in this area because it ultimately represents a phasor. And so this we can relate now with just a little tiny bit of manipulation to the velocity. Okay, and then we still now have this length of the time chirp, right? The time of the chirp, but with that velocity. So then we can rearrange this equation and come up with a measurement of the velocity based upon this change in phase between two successive pulses, right? Where these pulses are spaced at approximately TC. Okay, so now that maybe assumes that as soon as we're done transmitting, we can start transmitting again, right? There's no gap between ending here and moving the synthesizer back to this frequency and starting again, right? So you got to decide whether that's realistic or not, but it's awfully close, right? So all right, so by measuring phase, we can estimate the velocity of a target, right? So we do that over two successive pulses of this chirp. So, but as I hinted, phase measurement is only unambiguous within plus or minus 180 degrees, right? So if you've moved more than a wavelength, you're going to wrap your phase around and stuff. And so if you moved too far within that time of the successive pulses, the two pulses, chirps, then you're going to get a measurement ambiguity, and your phase might be really 540 degrees, but you think it's 360 less than that, right? So so you would estimate your velocity to be much slower because you didn't realize the phase wrapped. Right, so that sets an upper bound on our velocity, right? So now we can calculate that, and that turns out to be the wavelength divided by 4 times this chirp time, right? So so that might be something. It's how fast of a target do we need to be able to calculate? Well, if you're looking at another vehicle and it's coming towards you, or it's crossing in front of you, or something like that, you've got to do some calculations to decide, are we going to arrive at the same point on Earth at the same time and therefore collide, and all the consequences associated with that, right? So you've got to be able to track vehicles up to a certain max speed, right? So that's going to then, assuming you're stuck with a particular lambda, that's going to directly determine your length of your chirp, right? So now, understand though that was all for a single target. If we have multiple objects out there, multiple targets, then we're going to have multiple signals coming back. And the phase from those will all sum at the antenna, right? So now how do we resolve that, right? So the phase is going to be affected by both targets. And even when we go and look at that frequency bin, we're going to get phase contributions from the other target. So the solution is to transmit a frame of n equispaced chirps. Okay, so we already needed 2 to make this velocity measurement, but now let's transmit a whole frame of these things. Well, we're going to constantly be transmitting them, but let's collect up n of these things and put those into a vector matrix and analyze them together, right? So it turns out that the phasors of the signals, we can look at these phases that are these phase differences associated with the velocity for each target. They're going to rotate as a phasor, right? Remember back to probably your second semester circuits class when you learned about phasors, right? So you know, it's going to be rotating at a certain rate through you know, phase, and that phase rotation is essentially a frequency, right? So that's why we're using omega to represent these. So the phasors of the signals from each target rotate relative to their velocity. Now, we use that to perform a Doppler FFT on the phase of the first FFT, right? So back here, we took a Fourier transform and to get the distance, right? And at first we only looked at the magnitude, but then we knew that well, we had phase that comes along for free, so let's use it. Now let's collect up not just signals from a you know, a single chirp, but let's collect up a whole bunch of them and now perform FFTs on the phase from the first FFT, right? So what is that going to look like? Let me draw that real quickly here. And so we might have a matrix here. That's my time. Okay, so we're going to take these signals and we're going to then perform an FFT, and that's, we're going to store complex values in each of these frequency bins associated with this fast Fourier transform, right? And so these are all complex values. We can read out the magnitude or we can read out the phase, right? And then we're going to send another pulse, and we're going to do that again, collect up a frame of that information. And then we keep doing that. So we're going to have all these different pulses, right? And there's n of these. And so then we'll have n of n rows, right? Now, if we find through our original distance FFT that, hey, there's a target out in this area right here, right? And so now let's look at the phase in those, that phase difference, and do an FFT in this dimension, do it along those, right? So now we are able to identify different peaks in this, what we call the Doppler spectrum, right? So these guys, now when you take this, that's going to produce some sort of spectrum, and we'll out of this second FFT, and now we can look at that, find the peaks of these, and then calculate the velocities associated with each of these, right? So now, so what we did is we started looking at phase, and we looked at the phase between two successive pulses, and that from that we learned how to determine velocity. But then we realized that to track multiple targets, we need to separate them out again to gain resolution. So we do that through another Fourier transform. But now it's this Fourier transform in the other dimension. It's almost like a two-dimensional Fourier transform. But really we're kind of doing these rows in real time in succession. And then once we have a frame of these, then we can do this velocity calculation where we separate out the targets in velocity in this Doppler spectrum, right? And then we just use those equations that we derived quickly. I didn't go through every step of them, but if you go back and try to derive them, you find that they fall out very directly. They're not complicated. So now we look through this array with this Fourier transform and find the peaks in there. And each of those peaks, we go and look at the phase there and relate that back to the velocity. So now we have an ability to look at our this delta W, delta omega, and relate that to our change in velocity that we want to be able to recognize, and given a chirp fine length, right? So this, if we're able to resolve delta W in this Doppler domain, Doppler spectrum, then we can resolve that small difference in the velocity. We can tell whether someone's going 55 miles an hour or 70 miles an hour, right? So, and we, again, through the properties of the Fourier transform, that's going to be related to this n, where n is now this length of the overall, what we'll call a frame, right? So now we have all these chirps here, each TC long. We've got n of them, so this total frame is n times TC, right? And so now our frequency resolution is needs to be be only as good as 2 pi over n, right? So if we need finer resolution, we need a longer frame, right? So so yeah, restated, delta V is going to be greater than your wavelength divided by this total frame time here, right? So so at this point now, we figured out how we can isolate targets by distance and velocity, okay? And so what about angle of arrival, right? So we haven't talked about which direction these things are in yet. So turns out we can resolve the angle or bearing to a target by adding multiple antennas, okay? And if you've studied a little bit of antenna theory, array antennas, this should not be surprising to you. You'll see some of the similar type of notations. We've got a transmit antenna out here, and now we have two receive antennas. This distance from this target object back to this antenna is D, and this is D plus delta D, right? So there's some additional distance that is traveling, okay? So the phase at each angle will vary as a change in that path distance, right? As this signal is traveling from here to there, that's some number of wavelengths and fractions of wavelengths, and then that affects the phase at which we arrive at this antenna. This guy, in this case, this guy's to the left of the center line between these two antennas, so this path is going to be a little bit longer. So it's going to go through another fraction of a wavelength before it signal arrives here and it gets converted into currents in this and processed, right? So and so we can relate that phase again by this fraction of a wavelength, right? Now here, this D is not a round trip. This delta D is not a round trip. This is just distance from here, from the target to the antennas, because this is a common signal, right? This is a signal transmitted from the transmitter to the object, and it's only at this point do our distances vary. So we lose that factor of 2 that we saw in the analogous earlier slides. So now that's a terrible drawing because it's not to scale, right? So this is a little bit more to scale, and meaning that these guys are really closely spaced together compared to how far away these this target is, right? And so that these lines are approximately parallel, right? So now we can use some little trig, and we can find the right angle between the right angle distance between these, and relate that to the physical spacing of these antennas, which I call L here. I got a lot of this information from some TI application notes and some videos, and they use D there, but I find that confusing because we've used D in this range out here also. So I could have changed all those to R's, but it's easier to change this to L, right? So if you read some of the other references, you'll see them use D here. But a little basic trig here, and that's a right angle there, and this is theta. Well, what is that theta? That theta is this angle with respect to this normal to this spacing between these guys, right? So these antennas. So it's that angle at which we're arriving. That's what we want to know, right? And but that with your geometry, hopefully you remember that that is the same as this angle right here, right? So we know this distance. That's physical. That's what we implemented on our module, our chip, or whatever, right? And then we know we're solving for this angle, so we can relate this distance here. This is the additional distance that it travels, that this signal travels to this antenna beyond this one, right? So this is L sine of theta. And so that's assuming these lines are parallel. Now, so with a little bit of manipulation here, again, the same concept where this phase here, these signals are related to the fraction of a wavelength that we're traveling, okay? And that distance here, that fractional distance is L sine theta, but it's normalized to a wavelength because we're looking at fractions of wavelength and scaling it by 2 pi radians, right? So yeah, just solve for theta, and you end up with this in terms of an arc sine, inverse sine. So note that this is nonlinear. Before, everything was nice and linear. Now we've got this nonlinearity. So what's the implications of that? Okay, I'm going to wrap up here. Not a great place to stop. Maybe another slide or two. But there won't be there's not any homework yet on this class. I want to look at your homework 3 and stuff, and then homework 4, and also and I know I told you to deprioritize those homework assignments for your projects and your research reports, and so yeah, I'm going to let everything slide. I'm going to once I'm finished with this lecture, and I'm just with this FMCW, I'll come up with a little design assignment that helps you implement work with these equations, right? So it should be easy and fun, but we'll do that next week. So all right, so I'm just going to stop there and also talk about your the Holman filter. So again, if you're an undergraduate, you should pick a language. Might be MATLAB, might be Python, might be C++, and pick a implementation. If it's MATLAB, you can use the Coleman function out of the toolbox and run an example. Just get your hands dirty with it, right? Just don't like plug and chug and turn it in. You know, I want to see that you are actually working with it a little bit and understanding it. If you're a grad student, you know, looking for a little bit more ambition there and actually take a stab at trying to implement it, you'll find tons of code to start with. So I'm not expecting you to start from zero there, but actually go through the process of implementing it. I think that'll help cement that whole idea of things in your mind and stuff. So all right, keep checking Moodle. I put up references. I hope that you guys can look at those videos and other references. It's not a ton of stuff. I try to keep it to a lot of videos, and I think that really helps your understanding. Again, this course you're going to get out what you put in out of this course. So we'll see you next